8.5 Determinants and Cramer's Rule. Maybe I should start with the good news. This is our last section in Chapter 8, our last section of matrices. But once again, we have one more way of solving a matrix. So far we can use our Gauss elimination or Gauss-Jordan if you want to. We have our inverses that we learned in the last section, and now we're going to do Cramer's Rule. All of them are valid ways to solve a matrix, and sometimes it's just determined which way do you prefer, or sometimes you're going to learn by what you see and what you know you can get. You can kind of choose like which way is my preferred method, which one would work better for this problem. So there are advantages and disadvantages to each method, but I do want you to be fluent and understand how to do each of these methods. So let's go through Cramer's rule and using determinants and what that means. So a little bit of, I don't know if you want to call it terminology or even by sight what this means. I know when we started matrices at the beginning of the chapter, I made sure to tell you that when you see just a matrix and you're writing just a matrix, you should use these bars with kind of the indents as well. Put those there. If you only draw the bars around it without putting the indents, that means that you are looking for the determinant. And the determinant of a matrix is actually a value, a number of some type. So if you only see just those bars, you're actually looking for the determinant, which should be a number. All right, so some things to make sure we know about determinants. Number one, we have to have a square matrix to be able to find a determinant. A 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5. You cannot have a non-square matrix and find a determinant. So determinants only belong to square matrices. And depending on the type of determinant, the type of the size or the order of a matrix can determine on how you can find the determinant. Okay, a 2 by 2 matrix, there's really one way, and usually only one way we ever say to find the determinant. And when we are finding that, what we're going to do is we are going to take the product of A1 times B1 and subtract the product of, A1 times B2 and subtract the product of A2 times B1. I'd like to call it multiply the front diagonal and subtract the back diagonal. Not really technical terms there, but that's how I like to think about it. Okay, and remember this is only for a 2 by 2 right now, but it is a pretty simple step. So when I'm finding the determinant of these two matrices, I'm going to take the front diagonal and I multiply it together, so -5 times -7, and I'm going to subtract the back diagonal, which is -1 times -2. So -5 times -7 is 35, minus -1 times -2 is 2. I subtract, and I get a determinant of 33. That's my determinant. All right, pretty easy stuff. Can I make it a little bit harder? Slightly. We can make uglier numbers, right? So for number 2 here, front diagonal, I have 2/3 times 3/4. And I'm going to subtract the back diagonal, which is 1/3 times -1/2. The order in which we multiply doesn't matter. That's a commutative property, but we definitely need to make sure we do front diagonal minus back diagonal. You cannot flip-flop them. You will get different answers. All right, 2/3 times 3/4. My 3's can cancel. My 2 and 4 can simplify to 1/2, so I have 1/2 minus. Over here, I can't simplify anything. 1/3 times -1/2 is going to be -1/6. To subtract them, I do need to have a common denominator. I can turn 1/2 into 3/6, and 3/6 minus a negative becomes plus. 3/6 plus 1/6 becomes 4/6, and I can simplify that into 2/3. And there's my determinant. All right, that's a 2 by 2. Not too bad, pretty easy to figure out. Okay, so what is the value of being able to find a determinant? Well, we have Cramer's rule that was developed by using, excuse me for that little squiggle there, that was created for using this determinant rule is Cramer's rule on how to solve a system of equations or a matrix. Okay, so to solve using Cramer's rule, we have our system of equations here, and I end up with 3 different matrices I'm going to create, and I'm going to find the determinant of. we have our originally determinant, which is your coefficient matrix. Okay, I'm going to see if I can write these without and keep it legible. So your coefficient matrix is going to be what we would call our D or our determinant. We want to be able to define a dx, and this is going to help us in solving for the variable x. It's still going to be a matrix, but we're going to replace our x column with the answer values. That's my second matrix. My third one would be dy, and in that one, we're going to take our original matrix and we're going to replace the y column with the answer values. It really helps if I could spell. And then to find our value for x, we're going to find the dx and divide it by our d, and to find the value of y, we're going to do our dy and divide by d, and that'll help us solve. Okay, so let me see if I can extend my paper here a little bit. I don't know if I have much room, a little bit. And then we're going to see if we can get all our work here so we can use this Cramer's rule to solve our system. Okay. So our first thing from our system is we want to find our D matrix. So to find our D matrix, that is just our normal matrix. We're not going to augment it. We're just going to do just the coefficients. So on my first equation, the coefficient of x is 3. The coefficient of y is -4. On my second equation, the coefficient of x is 2. And the coefficient of y is 2. And there's my D matrix. I'm going to use this to now define my determinant. So my determinant is my front diagonal, 3 times 2, minus my back diagonal of -4 times 2. So I get 6 minus -8. And when I do minus a negative, it becomes plus, and I get 14. So my D is going to be 14. Now, right now, it's not part of my solution, but it's going to help me find my solution in a little bit. Okay, moving on, we're going to find our dx now. Okay, so to define dx, the rule, or if you do this, and you'll notice it's here in this note, is they replace that first column with my answers. Okay, that's what I said over here as well, is I replaced my x column with my answers. So I look at what I had before with my D, which was 3 and 2 in the first column. Instead, I'm going to put my answers, so I'm going to put 4 and 12. But my y coefficients are still going to stay in the same place, so I still end up with -4 and 2. And now I'm going to define the determinant of this matrix. So my front diagonal is 4 times 2, minus my back diagonal here, which is negative, I don't know how to get rid of those. Okay, which is going to be -4 times 12. So I get 8 minus -48. When I get rid of my minus a negative, which becomes plus, I'm going to get D of x equals 56. Okay. So now, because I have a D of x and I have a D, I can solve my x because my x is going to be dx divided by D. So my dx here is 56. My D was 14. If I do 56 divided by 14, I get 4. That is my x value in solving my system. All right, one more to go. And we need to find our dy. So for dy, I go back to my original matrix back with the D, okay? And again, notice I'm back to my original A's, okay? My original x coefficients of 3 and 2. We're not working off the dx one, we're going back to the original, so I leave 3 and 2 in the x column, but I replace my y values with my answers. Okay, so now I put that same set of answers of 4 and 12 in for my y's, and I work on my determinant for this matrix. So I get 3 times 12 minus my back diagonal, which is 2. So I get 36 minus 8, which leaves me with 28. And that's my dy. I'm going to try to squeeze this in here in what little bit I have left. So to find my y here, I'm taking dy divided by d, which is 28 that I just found, divided by my d from earlier, which is 14. And I find that my y is going to equal 2. So I found my solution of this system. The would be 4, 2, okay? 4 is my x, 2 is my y, and if I check, 3 times 4 is 12, minus 4 times 2 is 8, 12 minus 8 is 4. Works for the first equation. Second equation, 2 times 4 is 8, 2 times 2 is 4, 8 plus 4 is 12, works for the second. So that's a quick, simple example of Cramer's rule using these determinants. And when we find the d determinant, the dx determinant, and the dy determinant, we can solve for our x and our y variables. All right, let's move on. All right, a couple notes here on the top of this next page, and this applies to any size matrice, but especially on a 2x2, it's easy to look at and such. If you get a determinant of 0, especially if your d determinant is 0, you have a problem because you can't divide by 0. But if you get a d of 0, it's possible. What you need to check, though, are the determinants, your dx and your dy. Because if one of them, at least one of them, is not 0, you're going to end up with the no solution. However, if you get d equals 0 and then all the other determinants are also 0, then you're going to have your infinitely many solutions. Okay, so that's kind of one of these things when we work with Cramer's rule. So be careful and make sure, number one, you check your math to say, did I really get a 0? But you can't just stop at d equals 0. You've got to try your dx and your dy to see if you get something other than 0. All right, so let's try our example 4 and see what we get. So first things first, why don't we write these equations in order so that we don't mess up on our signs and stuff. I'm going to make this 2x minus 3y equals 7. And it looks like my second one's okay, 4x minus 6y equals 3. If your equations are not in that format, you could mess up the signs, especially on your matrix. So make sure your equations are in the right order. Okay, so I'm going for my d determinant first. So this is just the straight up coefficients. I got 2 on my x, negative 3 on my y. I have 4 on my x and negative 6 on my y. And I'm good for my values. Working on the determinant, front diagonal is negative 12 minus my back diagonal, which is also negative 12. And when I do negative 12 minus negative 12, I get 0. So I know that I'm going to have a special solution, either no solution or infinitely many solutions, but I need to keep checking. Okay, so when I go to check, I'm looking at my dx next. Remember, on my dx, I'm replacing my x column with the answers. So I'm going to put 7 and 3 here. I leave my y column where it was, negative 3, negative 6. And here's my new determinant for dx. Again, determinant. My front diagonal, I get negative 42. And subtract my back diagonal, which is negative 9. Negative 42 minus a negative 9. And I get dx equals negative 33. And just so we can have this, I'm going to go ahead and also get my dy, although I pretty much know what my answer is going to be. For dy, again, I would leave my x column as is, 2 and 4, and replace my y column with the answers, so 7 and 3, and go ahead and get my determinant. I get 6 minus my back diagonal of 28, and I get my dy equals negative 22. Because I get one determinant is 0, my d is 0, my dx is negative 33, and my dy is negative 22. I have the first scenario where not all of them are zeros, so I definitely get a no solution here. If all of them were zeros, we would have the infinitely many. Quick note, if your d is a value other than 0, and dx or dy is 0, that's fine, because if your 0's in your numerator and you divide by some whole number, there's no problem with that. Your answer will be 0 for that variable. So remember, it's okay if dx or dy are 0 and d is not. But if the problem comes in when your d is 0, then it narrows you down to the no solutions or infinitely many. All right. Let's move on to the 3x3s. Okay, so definitely a little more work on the 3x3s when we go on to this one. So a couple things, you'll notice the rest of this page is just kind of notes, and so some things I want to show you. First, I want to kind of state, if you found determinants in Algebra 2, my guess is what you did, and I'm going to make up some numbers here, so don't copy them. I'm not going to really do the math. Let's say you had coefficients of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. When you found your determinants in Algebra 2, I believe the method you did is you did where you repeated the first two columns. So you put a 1, 4, 7 here, you put a 2, 5, 8 here, and to find the determinant, you found all your front diagonals and added them together. So you found a product plus a product plus a product, okay, of your front diagonals. Then you went backwards on the three full diagonals. So you had a back diagonal, and a back diagonal. There were three of them. You found all those products and added them together, and I'm just messed myself up here. Make sure I don't write this wrong. You found all of those products and added them together. And then what you did was you subtracted them. And that is a method of finding your determinant on a 3x3. We are not going to use that in PreCalc here, but I do want to remind you that's what you did, and it's fine. That is one thing you can do. And by the way, that is what you see right here, okay? You see those triple products where you have three numbers you multiply together, and then you subtract the back ones. That's why you see this. I called them all, add those together when you had those products, but you could just do minus the 3 as well. So that is definitely a method you could do. Okay, we're going to do something slightly different by our 3x3. And what we're going to do is, let's see if I can kind of pick this out for you. If you see, what I'm going to do is choose a column. Okay, and I'm going to choose this first column so you can kind of see where this is coming from. Without numbers, it's a little harder to see, but I do want to state this. They chose the first column, A1, A2, A3. Okay. Notice in here, my first one has an A1, and my this one back here has an A1. So what they did is they factored out that A1, and they left what was left here and here, okay? So they have this in the middle. Then they found their A2s, so that's my second element here, and I have an A2 here, and I have an A2 here. And again, they factored the A2 off, and they left what was remaining. And then the last one, I have an A3 here and an A3 here. They factored that off and they left what was remaining. And what this ends up being is called expansion by minors is what we're really doing here. Okay, I know without numbers, I know what I'm saying right now is probably super, super confusing. Okay, but what ends up happening is we're going to take these values, we're going to leave them in the front, okay, and we're going to take small determinants, because what this ends up being is what's being subtracted here, here, and here are the small 2x2 determinants. So it keeps our numbers smaller and such. Okay. I know I've lost you. That's fine. Don't worry about that. This is one thing I do want to stress though. We can use this method, but I need you to remember that we're going to have a checkerboard of signs. Again, I'm losing you right now. Just kind of keep nodding your head and going, okay, okay, okay. As I tie this all together, hopefully this will make a little more sense. My first element is always plus, then a minus, then a plus. Because I'm doing a checkerboard, my next one is minus, plus, minus, plus, minus, plus. Okay? Just remember that the elements in those positions need to carry those values. Okay? So if you need to write that at the top of a quiz or test sometime, just remember that's how our signs are going to go when we do this expansion by minors. Okay? And remember, it's okay right now if you're lost. Hopefully by the time I get done here with the next few examples, it'll start making a little more sense. Okay, next page. Okay. We're going to do finding the determinant by the expansion by minors. Okay, so as I stated in the other page, we're going to choose 3 values. Okay, for ease on this first example, I want to choose the first column. Okay, one important thing I want to stress, columns. Okay, we're choosing a column. Don't choose to do this. So we're going to go for a column. We're going to choose that column, and we're going to separate these out and make these smaller 2 by 2 matrices to find the determinant of. Okay? The notes are there. I think walking you through it is going to help more than trying to go through those notes there at the top. But if you need to, go back up to this box of notes so that you can kind of read it. Okay, so let's get our space ready. We're going to do the determinant of this matrix by expansion by minors. Okay, so here's my first one. We're going to start on this first example with the first column. I just want you to know that you get to choose your own column when you do this, but we are going to start with the first column. So, quick side note from the other page, I know I get a plus minus plus, a minus plus minus, a plus minus plus. Again, it'll make sense in a minute. And I'm going to start with my first column. That's the column I'm going to use the expansion by minors. So my top element is a plus, the next one's a minus, the bottom's a plus, and I'll come back to those numbers. Okay, here's what we do on our first one. I am going to write my matrices over just so you can see this, and especially because I want them to still show up later when you look at these notes. Okay, when I'm starting with my first element of 3, I'm going to put this plus 3 out front here. The plus comes from here, the 3 comes from its value. I'm going to cross off the row it's in, I'm going to cross off the column it's in, and what's left is my new matrix. 4, 0, 3, negative 5. Okay. Let's go to the second one. I'm just going to keep going and then we'll figure out the value at the end. So once again, I'm going to rewrite this so you can see them. Okay. Now I'm going to work on my second element, which is this negative 3 right here. Okay. That's the one I'm going to work off. I'm going to cross off its row. I'm going to cross off its column. That negative 3 is going to come out here. Now, negative 3 comes from there, but this is also a negative, so I'm going to get a negative 3. And its remaining matrices are these 2 rows, 1, 0, 3, negative 5. These are the minors, okay? And finally, my last one, again, I'm going to rewrite it just so you can see everything that's coming from this. Okay, so I'm on to my last element, this one on the bottom, so I'm going to cross off its row, I'm going to cross off its column. That number was negative 1. It has a plus in front of it. And what's left in my matrix are these 4 values, 1, 0, and 4, 0. Okay. Give you a minute to absorb what I just did there. So I took my column, and I take each element in the column with its correct sign out front, and then take it as a scalar times what's left. I shouldn't have called it a scalar. I don't want to multiply it through. Just leave it as a coefficient maybe right now. Okay. Now this is what we're going to do next. We're going to work on determinants. Okay. So I'm going to leave this 3 out front, and for determinants here, I'm going to take my front diagonal of 4 times negative 5 and subtract my back diagonal of 0 times 3. Okay. Over here, this value right here is going to become plus 3, and then I'm going to work on the determinant. 1 times negative 5 minus the back diagonal of 0 times 3. All right, my next value right here of negative 1 times the determinant of 1 times 0 minus the back diagonal of 0 times 4. Okay. Let's keep going on numbers. This 3 is a coefficient. I have negative 20 minus 0. That equals negative 20. I have negative 5 minus 0. That's negative 5. I have 0 minus 0. That's 0. I get negative 60 minus 15 minus 0. So I get an answer of negative 75. That is the determinant of this matrix. Okay, so that's an expansion by minors. Now, I'm going to do one more quick thing here. I chose the first column. You don't have to choose the first column. I'm going to stress choose a column. I'm going to do this problem one more time, but I'm going to choose a different column. I think I'm going to choose the third column. So peek at this matrix right here. 3, -3, -1. Second column is 1, 4, 3. The last column is 0, 0, -5. Think about it if I choose this last column. Remember, the number in the column becomes the coefficient. So when I take this first 0 up here, which by the way is in a positive spot, it's minors, okay? I'm not going to cross them off because I don't want to rewrite it, but I'm crossing off the top row and the third column. I'm left with -3, 4, -1, 3. My second element is going to be a -0, and its remaining elements are going to be 3, 1, -1, 3. And finally, the last one is a -5, and it has a positive value. And its remaining are going to be 3, 1, and -3, 4. Well, this one's not going to matter. I'm multiplying by 0. This one's not going to matter. I'm multiplying by 0. I only have one I really need to do the math on. So I have a -5, and I'm going to get a 12 on the front diagonal minus my back diagonal of -3. Well, that's going to add together to make 15. So I get -5 times 15. I get -75. That's the same answer I got over here taking the first column. It doesn't matter which column you use, you're going to get the same answer. When you do this expansion by minors, you get to choose which column you want to use the elements for. I'm going to be honest, if I see zeros, I'm going to go for that column. It takes out a lot of the work, it makes my work go faster, and that's the one I'm going to use. So I used the first column the first time to show you a full process. And by the way, not all matrices will have zeros. But if you have zeros in your column, grab it. It makes for a real quick, easy determinant. Okay? One more page to go. And we are going to use this method of finding a determinant of a 3 by 3 to do Cramer's rule on a 3 by 3 matrix. Okay? So we're thinking determinants by this expansion by minors, and then we're going to use Cramer's rule to do, instead of just dx and dy, we're also going to do dz. Okay? And again, keep in mind that this process could be used for a 4 by 4 by adding a dw in there or something like that, whatever we need if we made bigger matrices. All right, let's start with our D matrix. And we are going to go for our expansion by minors. So we're going to start with our D matrix. So for D, we're going for coefficients only here. So we get 4, -5, -6, 1, -2, -5. Be careful on this third equation. I have 2, -1, and 0. There is no z on that one. Okay. Now, I have my determinant. I'm going to do an expansion by minors to find the value of my determinant. Okay, let me switch colors here a little bit so we kind of figure out what we're doing. Our choice, what column do you want to work with to find the determinant? Well, if you remember my hint from last one, if you can find a column with a 0, it's probably going to be a little bit easier. Okay, so I'm going to choose to do my expansion by minors with my third column because I see a 0. Okay, quick reminder, plus, minus, plus, minus, plus, minus, plus, minus, plus, when we look at our values. Okay, I'm going to start with -6. If I take and cross off the row of -6, cross off the column with -6, my only 4 elements left are going to be 1, -2, and 2, -1. I go to my second element, which is my -5. That is in the negative position, so I'm going to do negative of my -5. And when I cross off its row, that second row, and the third column, the elements that remain are 4, -5, and 2, and -1. And then my final element is 0 when it is in the positive spot. And if I crossed off its row and its column, I'd be left with 4, -5, and 1, -2. And I'm going to be honest, if you don't write this last one, because it goes to the 0, you can just skip it. But I do want you to remember that a normal expansion by minors should have 3 values. If one of them's a 0, obviously that one's going to disappear. All right, finding the values here. I have negative front diagonal is -1 minus my back diagonal of -4. A minus a -5 will become a +5. My front diagonal is -4 minus my back diagonal of -10. All right, let's clean up some math here. -6 is on the outside here of a minus and negative is going to be +3. +5 is on the outside, -4 minus a -10. Again, minus a negative is a plus, is going to be 6. I get -18 plus 30, so I get a value of 12. Okay, so D equals 12. And remember, this is the value we're going to use over and over to find the rest of them. I can't stress enough, please take your time to be accurate, because it is going to pay off. If you get your D wrong, it really causes trouble later on. All right, 1 down, 3 more to go. So let's get ourselves some space here, and let's keep moving. Okay. Trying to figure out how to keep this kind of the most organized I can. Okay, we're going to go to dx next. So in dx, I'm going to use my same matrix I used above, except my x column gets replaced with the answers. So instead of 4, 1, and 2, I'm going to use -1, -12, and 7. The rest of my matrix will stay the same as I had before. So -5, -2, -1. My y values don't change. My z values don't change, and I'm going to leave those as is. And I'm ready to find the determinant of this dx matrix. Okay, once again, our choice when we expand by minors to find which column we'd like to work with. Again, personally, I like something with a 0. I'm going to once again choose my third column. So it's going to look very similar to up above, but remember, because we switched that first column, we will get different values now. I'm going to start out with my -6, which is in a positive position. If I cross off its row, which is row 1, and its column, which is column 3, I'm left with -12, -2, and 7, -1. I go next to my -5, which is in a negative position, so I get -5. Remember, go back up to that top note if you're not sure what position you're in, and we're in a negative position. I cross off its row, the second row. I cross off its column, the third column, and the elements that remain are -1, -5, and 7, -1. And finally, the 0's in the positive position down there. And if I cross off its third row and its third column, I'd be left with -1, -5, -12, -2. But once again, this one will not matter because 0 times anything is 0. So I really didn't need that, but I do put it down there for someone who's trying to follow where we're getting these numbers. Let's do the math. -6 hanging out front while we do the determinant. My front diagonal is +12 minus my back diagonal of -14. My -5 becomes +5, which is my coefficient before my determinant. My front diagonal, -1 times -1 is 1, minus my back diagonal of -35. All right. Little math here. 12 minus a -14 becomes 26. So I have -6 times a 26. I get 5. 1 minus a -35 becomes 36. -6 times 26 is a -156. 5 times 36 is a +180. I subtract those two values, and I get a dx of 24. Okay, so dx is 24. I'm going to go ahead right now and solve for x. Remember, x is dx over d. So that's a 24 over my 12 from earlier, which means I'm going to get 2 for x. Now, will every answer be a whole number? No. But I do want to stress to you, I'm going to be honest, if I'm choosing one of these for a test or quiz, I'm going to try to use cleaner numbers. So if you're not getting a whole number, go check your determinants and see if you made a mistake somewhere. All right, how much more room do I have on this paper? Yeah, I've got a little bit. Okay, we've got our dx. We're going for our dy. Okay. So for dy, I think back to my original matrix on my d. My first column was my x. That can stay the same, so I'm going to go back to my 4, 1, 2 on my x. This time I'm replacing my y with my answers. And my answers are -1, -12, and 7. And my z's, I'm going to keep the same thing, so I'm going to keep it at -6, -5, and 0. The only one I switch on my dy is my y column, okay? Remember, answers on my x, answers on my y. Those are the ones I'm switching. The rest of them stay the same, okay? All right, once again, I'm doing expansion by minors. I get to choose which column I want to use. And I'm going to be honest, I want to choose a column with zeros. If I have them, it takes out some of the work. So once again, I'm going to choose my third column. All right, so I'm going to do -6. It's in a positive position. I cross off its first row, its third column, and I'm left with 1, -12, and 2, 7. My next element is -5. It's in a negative position. And when I cross off its row and its column, I'm left with a 4, -1, and a 2, 7. And my 0 is my last one. If I cross off its row and its column, I would be left with 4, -1, and 1, -12. And once again, that one is not going to matter, but I'm just putting it out there for you. All right, some math to do. -6 is my coefficient. Working on the determinant. Front diagonal is 7 minus the back diagonal of -24. Remember, I get the product to find those. My minus -5 becomes +5. My front diagonal on this one is 28 minus my back diagonal of -2. Little math here. -6, 7 minus a -24 becomes a +31. I get a 5. 28 minus a -2 becomes a +30. I get a -186 plus a 150 gives me a -36, and that is my dy. All right, so if my dy is -36, to find my y, I take dy and divide by d. That means I have -36 divided by 12, and my y is going to equal -3. All right, one more to go. I need a new piece of paper, so I'm going to lose seeing this work right here, but let's go and let me get a clean spot to find my dz. All right, so to find my dz now. So remember, since this is my z, I go back to my original d, and I want my x coefficient, so I'm going to keep the 4, 1, 2 from before. I want my y coefficients back, so I want my -5, -2, -1. And this time I replace my z coefficients with the answers because I'm on my z one. So now I get my -1, -12, and 7. So there's my dz matrix. And I wanted to find the determinant of this one. All right, just like on the rest of them, I want to go ahead and find which column I want to use to do the expansion by minors. Well, I'm going to be honest, I don't have any zeros anymore on this one. So any column's good to go. The question is, which numbers look slightly cleaner? There's no wrong answer here. I'm going to choose the first column, but to be honest, any one of them should work. Just make sure you grab it, okay? So I'm going to choose the first one, but remember, there's no wrong answer. Okay, so I'm going to do 4, and that's in a positive position. So I'm going to leave a +4 out front here. And if I crossed off its top row and its first column, my remaining elements are going to be -2, -12, negative 1, and 7. When I go to my 1, remember that one, it's in a negative position, so 1 is the coefficient, but it's in a negative position, so it gets a minus out front. And if I cross off its row 2 and its first column 1, my remaining elements are negative 5, negative 1, and negative 1, 7. And finally, my last coefficient is going to be 2. It's positive position. And if I cross off its bottom row, the third row, and its first column, my remaining elements are negative 5, negative 1, and negative 2, negative 12. Okay, so we have a full expansion this time. I don't get to cross anything off because I don't have any zeros. Let's go ahead and do the math. My first one has a coefficient of 4. My front diagonal is negative 14. Subtract that back diagonal, which is 12. In the middle, I have negative 1. Its front diagonal is negative 35, minus the back diagonal of positive 1, plus 2, and its front diagonal is positive 60, minus the back diagonal of positive 2. 4 out front here, negative 14 minus 12 gives me a negative 26. Negative 1 times negative 35 minus 1 is negative 36. And finally, on my last one, 60 minus 2 is 58. 4 times negative 26 is negative 104. Negative 1 times negative 36 is positive 36. 2 times 58 is 116. And when I join all those up, I get 48 for my DZ. So if DZ equals 48, I will find Z by taking DZ divided by D. So my DZ of 48, back in my problem, my D was 12, which leaves me a value of 4 for Z. So when I look at my 3 variables, my X was 2, my Y was negative 3, and my Z was 4, and that will solve my system using matrices, using Cramer's rule, using expansion by minors because of the determinant. So something a little bit different. You did Cramer's rule back in Algebra 2, but you didn't use the expansion by minors, so that's a new thing for us. Does it save us time? Possibly. I don't know. But it's definitely something different, something I want to introduce to you, and something I want you to practice. So, back on the last page before I moved pages, I believe at the bottom of the page, if I ever got there, I had the homework down there. Not getting it to move very well here. There we go. Try page 866, 3 through 51 by 3s, or more importantly, do some of the odds so you can look at the back of the book. I really, really want you to practice this Cramer's rule and make sure you practice these determinants. So this is our last section of notes in Chapter 8. Just a heads up, when we take our test, I'm going to be specific and look for specific work to solve your systems. When I ask you for Cramer's rule, I want to see the determinants and I want to see Cramer's rule. When I ask you for Gauss-Jordan, I'm going to rephrase that. I'm not going to ask you for that. When I ask you for Gauss elimination with back substitution, I want to see that. When I ask you to solve by inverses, I want to see the inverse. So it's important that you're practicing every method. A lot of them have similar work, but I definitely, want to see those different methods being tried on each of these matrices. Good luck.